Welcome back to the Deep Dive. This is where we take those dense technical reports,
Yeah.
the regulatory blueprints,
Yeah.
all that competitive analysis, and we really just boil down to what you need to know.
Exactly.
And today, we're not just analyzing a market segment. We are taking on a mission. And it's a mission that's incredibly complex, very high stakes, and it really defines the future of affordable mobility, on a global scale.
That's a great way to put it. We're stepping right into the pressure cooker of product development. So for today, you and I were the chief systems engineer at a major global automotive consultancy.
Right.
Think of a client who wants to capture the entire low-speed EV market, from Beijing all the way to Berlin. Our job isn't to draw a pretty picture.
No.
It's to create the real executable engineering requirements specification, the SOR, for a brand new energy storage system, an ESS. And we're designing it from scratch for these micro low-speed electric cars.
And this is not a simple problem where you just, optimize for one variable. The whole mission is built on this intense, almost existential tension.
Yeah.
We're talking about global mass production. China, Europe, the US, Japan. And the challenge is trying to balance two goals that seem to just completely contradict each other.
And what are they?
Well, first, hitting an aggressive, almost unbelievable cost target. I mean, we are talking a pack cost below $100 per kilowatt hour.
That's incredible.
It is. And at the exact same time, you have to meet the most stringent, new, global safety and compliance standards the world has ever seen. It feels like, asking for a 5-star crash rating on a scooter.
It does. And what's so fascinating here is that the structural shift in this market, it's done. It's irreversible now.
What do you mean by that?
Well, for years, the micro-EV world, especially in China, it just ran on one philosophy: cost minimization. That was it.
Get the price as low as possible.
Get the price as low as possible, often, at the expense of safety, of quality. That era is over. The industry has moved. It's a decisive shift to a design philosophy that's anchored in compliance and safety. That's the pillar now.
So it doesn't matter how cheap it is if you can't sell it.
Exactly. If the battery pack can't get type approval in Shenzhen or Brussels, the cost is irrelevant. You have a very expensive paperweight.
So for this deep dive, we've taken this mountain of strategic blueprints, competitive teardowns, safety prognosis, all the high-level analysis you'd get from a firm like AVL or McKinsey, and we've translated it into a detailed, executable document.
The SOR.
The SOR. So our global engineering team can just pick this up and know exactly what to build, down to the materials, down to the software.
And we've already locked down the key architectural decisions that make this whole balance possible. The balance between cost and safety.
Okay, lay them out for us.
The foundation has to be the 96-volt to 150-volt low-voltage architecture. That's non-negotiable. Then for chemistry, you need a pragmatic dual-track strategy. So LFP lithium iron phosphate and the emerging sodium ion.
And the third piece?
Structurally. To get the efficiency and hit the cost metrics, we have to mandate CTP, cell-to-pack integration.
Okay, let's unpack all of that. But we have to start where all serious engineering starts, which is with the constraints. Because in this game, the rules aren't suggestions. They are the absolute non-negotiable design boundaries.
That's right.
Welcome to part one, the new global regulatory landscape.
Let's do it.
So when we talk about global standards, the conversation, it really always starts and ends with safety. And right now, China is the one defining what's next. So let's start with that seismic shift happening over there with the GB 3803.031 standard.
This is truly revolutionary, and it's mandatory. So if you were building a micro EV, say, a couple of years ago under the current 2020 standard.
GB 3803.031.2020.
Right. The requirement was, I'd say, relatively lenient. You needed to give passengers at least 5 minutes to escape the vehicle after a single cell goes into thermal runaway.
And 5 minutes is still an engineering challenge.
Oh, absolutely. But you can often get there with, relatively simple passive measures, thin mica sheets, some internal fuses, a really aggressive BMS alarm strategy to warn the driver.
But that 5-minute grace period is about to vanish. The new 2025 standard is coming, and it's draconian. But I guess necessarily so, right?
Yeah.
To deal with public safety concerns.
It is. The new standard demands zero propagation. And the engineering definition is stark. It changes everything.
Okay, what is it?
The battery pack must not have any external fire or explosion for at least 2 hours, and ideally indefinitely after that first single cell fails.
Wow.
So the whole philosophy has shifted. We're no longer just delaying the fire for an
You're
evacuation.
trying to block it.
You're engineering to block the fire and completely contain the thermal event inside that sealed box.
That is a whole different ballgame. 5 minutes is containment, 2 hours is total persistent thermal isolation.
It is.
And that has to dictate your chemistry choice right from the start.
It does. It immediately rules out certain chemistries just based on the physics. So high nickel, NCM, nickel, cobalt, manganese is effectively eliminated in a passively cooled micro EV.
And why is that? The energy release.
The energy release is just too high. When an NCM cell goes into thermal runaway, it releases two things: extreme heat and huge volumes of flammable gas. There is just too much energy to contain in a small, air-cooled, cost-optimized pack.
So this zero propagation rule forces you, no exceptions, toward a different chemistry.
Yes, high thermal stability chemistries, which means LFP, lithium iron phosphate, or sodium ion. Both of those have a thermal runaway trigger temperature that's way up there, over 270 degrees Celsius. So they're just inherently safer and easier to manage.
So even as we're trying to hit this $100 per kilowatt hour target, this new regulation is immediately adding cost and complexity.
That's the tension.
It pushes us to integrate components we have to have, even if they add to the bill of materials.
Precisely. To get to zero propagation, you have to integrate specific, costly, but totally non-negotiable components. First, aerogel insulation layers between the cells.
Which is a fantastic insulator, but not cheap.
Not cheap at all, but it dramatically slows down heat propagation to neighboring cells. Second, you have to design these precise directional venting channels and dedicated explosion-proof valves.
Right, because the gas has to go somewhere.
It has to go somewhere, and the physics of that venting is critical. You have to guarantee that the hot gas expulsion is channeled downward, away from high-voltage connections, and most importantly, away from the passenger cabin. And designing those escape channels adds a lot of complexity to the pack casing.
And even with all that, you can't forget about charging. Consumer expectations are moving fast.
Absolutely. The system has to align with China's GBT 2234 charging standards. And you look at a car like the Geely Panda Mini, and that's the signal. We're now competing against micro EVs that offer 22 kilowatt DC fast charging.
So our ESS has to handle that.
It has to handle continuous current over 100 amps. That means thicker, more expensive bus bars and much better thermal management, even with just forced air cooling. We have to engineer for tomorrow's consumer, not yesterday's.
Okay, so let's move west. Europe brings a whole different flavor of compliance. It's less about the physical fire and more about data integrity, traceability.
Yeah, that's a good way to put it. If you want European type approval, you start with the basics, like UNIS R100 revision 3. It still requires that familiar 5-minute warning for thermal runaway.
Okay.
But R100.03 also brings in a much more rigorous mechanical tests: vibration, mechanical shock. It demands a very high level of structural rigidity, which has a direct impact on our CTP design.
But the real hurdle, the thing that's going to define engineering strategy for years to come, is the EU battery regulation, the digital battery passport.
This is a massive game changer. Its strategic implications are just, you can't overstate them. It's mandatory by 2027 for basically any industrial or EV battery over 2 kilowatt hours.
Which is our pack.
Which is our pack. The ESS has to support data serialization, recording, and secure transmission of all this crucial data. And it has to be accessible via QR code right on the pack. It's an engineering mandate, but it's also a very powerful non-tariff barrier.
Let's unpack the data side. What exactly does our BMS need to record and transmit?
The list is exhaustive. It includes the carbon footprint ID from when it was made, detailed info on material sourcing, so the recycling ratio of cobalt, lithium, nickel, lead, and of course the current state of health. It's basically a mandatory, secure digital twin of the battery's entire life.
This is not just a software update you can patch in later. This impacts hardware selection, procurement, the whole thing.
Oh, absolutely. On the hardware side, our BMS, it can't just be the cheapest microcontroller you can find. You have to select MCU chips with enough flash storage to hold all this data for the battery's entire life.
And it has to be secure.
Critically, yes, it has to integrate a secure element or an encrypted engine. This is expensive hardware, but it's vital. It supports secure local storage and certified uploads to prevent data tampering.
So, people trying to cheat the system. Faking the battery's health to sell the car for more.
Exactly that. And this requirement pushes way upstream to our Tier 1 and Tier 2 cell suppliers. You can't build a passport if you don't know where the materials came from.
Right.
It mandates a revolution in supply chain documentation. Our procurement strategy has to demand that our suppliers, CATL, Gotion, whoever, provide third-party verified carbon emission data for the specific cells we buy. That has to be integrated into our product lifecycle management system from day one.
So if you're proactive about this, you have a huge advantage entering the European market.
A massive advantage. The cost of non-compliance is so much higher than the cost of a secure element chip.
Okay, that makes sense. Let's finish up across the Pacific, North America and Japan. Here, the focus seems to pivot back to structural integrity and preventing electrical hazards.
Right. The main U.S. standard, FMVSS 305, is really focused on preventing two things after a crash: electrolyte leakage and electrical shock. For our design, the key metric is electrical isolation resistance. After a 48 km/h crash, the DC system has to maintain an isolation resistance of more than 100 ohms per volt.
And for a light, cost-effective pack, that structural requirement is a core challenge. It has to survive a major impact and stay sealed.
It's a huge structural constraint. The pack has to stay physically intact, secured to the car, and it can't intrude into the cabin. And that's non-negotiable, even for a micro-EV.
And there's also UL 2580.
Right, which is voluntary, but it's the de facto benchmark for insurance and safety certification in the U.S. It often demands even tougher abuse tests, nail penetration, crush tests, external fire that go beyond even the new Chinese standards.
And Japan, with its history of small key cars, kind of combines all of this, right?
Exactly. Japan's regulations are close to UNR 100, but their domestic safety rating, JNCIP, demands achieving those high 5-star crash ratings, even for tiny cars.
Yeah.
And this is crucial for our design. It means the battery pack can't just be a box of energy. It has to be engineered as a structural component of the chassis.
So it actually helps absorb crash energy.
It has to participate in collision force transmission, absorb and dissipate that energy in a crash. This is really the starting point for cell-to-body, or CTB, integration. Our design has to be ready for that.
Okay, so to sum up part one, cost is completely secondary to compliance. Our ESS has to be zero propagation safe for China, fully data logged and secure for Europe's battery passport, and structurally tough enough to survive a crash for the US and Japan.
That is a brutal set of conflicting requirements. It is the ultimate engineering tension.
So now that we have the rules of the game, we can look at how the competition has tried to solve this puzzle.
Right. What they did right and what they did wrong.
So let's look at some real-world examples. If we're going to design the perfect, compliant, low-cost battery, we have to start with the undisputed champion of cost optimization, and that's the Wuling Hongguang Mini EV.
Wuling is a masterclass. They weren't just cheap, they were strategically cheap. And our analysis has to focus on their core decision, the low-voltage platform, specifically the 96-volt to 115-volt range. That choice is where the entire system cost optimization begins.
Okay, walk me through that. Why is that specific voltage range, that 96 to 115 band, so important for the bill of materials for the whole car?
It's the golden zone for this segment. It's this delicate balance that leverages component commoditization. So first, 96 volts is high enough. It's safely above that 60-volt threshold.
And why does that matter?
Because it significantly reduces the current you need to deliver a certain amount of power. P equals V times I. Lower current means you can use thinner copper wiring, lighter harnesses, smaller bus bars in the pack. That saves a ton on material costs.
And the other side of that balance, keeping the voltage low enough?
Critically, it stays well below 300 volts.
Wow.
And that matters because the vast majority of standard high-volume industrial-grade power semiconductors, your IGBTs, your capacitors that go in the motor controllers, they're rated for 200 to 250 volts.
So they're commodity parts.
They are mass-produced, highly commoditized, and therefore vastly cheaper than the high-voltage components like the 800-volt silicon carbide modules you need for a high-performance EV.
So the voltage wasn't just chosen for the battery. It was chosen to make the whole electric powertrain cheaper.
Exactly. It brings down the cost of everything. The charger, the inverter, the DC-DC converter, all the high-voltage wiring. And then for integration, Wuling's later models moved very aggressively into cell-to-pack, or CTP.
Right.
They were pioneers in getting rid of the heavy structural module end plates that were standard in older designs. Instead, they just used the box crossbeams for reinforcement. This improves your volumetric efficiency and it reduces the part count, saves on assembly labor.
And we have to adopt their supply chain strategy too, using multiple interchangeable suppliers, CATL, Gotion, CALB. That's a huge hedge against price spikes.
That multi-supplier strategy only works if we, as the systems engineers, dictate strict standardization upfront. So our SOR has to mandate standardized cell dimensions across all potential suppliers. That's how you maintain supply chain resilience and price leverage. It's essential to hit that $100 target.
Okay, now let's pivot to a bit of a cautionary tale. The Citroën Ami. This is a vehicle that really shows the limits of designing strictly to the edge of a regulation.
The AMI runs on a 48-volt, 5.5 kilowatt-hour system, and the core idea here was to leverage the European L6E classification, where any DC voltage below 60 volts is considered a safe voltage. And that's, it's very appealing to engineers and accountants.
So what were the benefits of staying under that 60-volt line?
The benefits were pretty compelling for simplicity and cost. Lower safety requirements mean that repairs don't need a high-voltage certified electrician. That's a huge saving in dealer training. Also, the electrical connectors don't need those expensive finger-proof designs. Every single connector, fuse, and terminal in that 48-volt system is substantially cheaper.
But there's always a trade-off. You can't cheat physics. Where did the 48-volt architecture just fail to meet consumer expectations?
It completely kneecapped the performance and the utility. The 48-volt system severely limits power, so the max speed is only 45 kilometers per hour. But more importantly, for our ESS design, the charging power is restricted to just basic 2.3 kilowatt socket charging.
Which is not enough anymore.
Not at all. Our analysis shows micro-EV consumers today demand faster charging. And 48 volts just can't efficiently support fast charging because the current draw would be enormous. The wiring and the thermal losses would be prohibitive. It's an interesting experiment, but it's a non-starter for mass market relevance.
And those upgrade expectations are perfectly captured by our next benchmark, the Geely Panda Mini. This shows us where the market is really going.
Absolutely. The Panda Mini, with its 17 kilowatt-hour LFP pack, it signaled a major market shift by including 22 kilowatt DC fast charging as an option. You can get to 80% in 30 minutes. That clearly tells us micro-EVs are now expected to be part of the modern EV charging ecosystem. Slow overnight charging isn't enough.
So what does that 22 kilowatt capability force our engineering team to do, especially for the thermal system?
It demands immediate and significant improvements in thermal dissipation. Even for our forced air-cooled system, the heat generated by 150 amps of continuous current is substantial. We need better air channels, thicker, high-voltage bus bars, and critically, the BMS software has to fully integrate the fast charge communication logic, specifically the GBT 27930 protocol that manages the handshake between the car and the charger.
And finally, let's look at some of the advanced suppliers who are solving these problems for us. The innovations from a company like SVLT with their short blade tech are super relevant here.
SVLT's short blade technology is perfectly suited for the tight space of a micro-EV. They use these long, thin, prismatic LFP cells. It's similar to BYD's blade, but optimized for smaller packs. And this form factor is exceptional for CTP integration because the cells themselves become the structural backbone of the pack.
But how does their safety design specifically address our toughest constraint, that Chinese zero propagation mandate?
They use something they call the thermal electric separation design. And this is a critical takeaway for our SOR. When a cell has a thermal runaway, the release of hot gas is explosive. If that gas blasts upward toward the electrical terminals, it can melt insulators and trigger a secondary short circuit, and then you have a catastrophic pack fire.
Right.
SVOT prevents this by putting the explosive vent on the bottom of the cell. The electrical terminals stay sealed on the top. So the result is that the force, the heat, the flame, it's all channeled downward, away from the critical high-voltage connections. It drastically reduces the risk of a secondary failure.
And the packaging advantage of mandating a short blade form factor.
It maximizes volumetric efficiency. In a micro-EV, the space between the wheels is so constrained. Using these long, flat cells lets us use that space way more effectively than traditional square modules or cylindrical cells. We can pack more capacity into that small wheelbase without raising the floor.
That is a comprehensive look at the landscape. We've got the regulations, we've benchmarked the leaders. Now it's time to synthesize this into the 3 core design decisions for our ESS platform.
Let's do it.
So the first, most foundational decision is the voltage platform strategy. We've seen why 48V fails. Why is jumping to a high-voltage platform also the wrong move?
We have to firmly reject 300-volt or higher platforms for this segment. The component costs are just excessive. You'd need expensive silicon carbide components for a car that's supposed to hit that sub-$100 per kilowatt-hour target. Plus, for small packs under 30 kilowatt-hours, the high cell count you'd need in series just creates these massive cell consistency management headaches for the BMS. Every cell is a potential point of failure.
So we need that golden zone again. the voltage range that perfectly balances efficiency, cost, and component availability.
And that zone is the 96V to 150V low voltage, high power architecture. So that's roughly 30 to 48 cells in series, which we call 30S to 48S if we're using LFP or sodium ion. And the reasoning is both functional and economic.
Okay, what are the key benefits of standardizing on that specific range? Why is that a non-negotiable in our SOR?
Well, first, it locks in the use of those cost-effective, commoditized 250-volt rated power semiconductors for the whole powertrain, just like Wuling did. Second, this voltage lets the system support competitive DC fast charging. We're talking 20 to 40 kilowatts, which we know is crucial for market acceptance.
Right.
And third, and this is important, it keeps the maximum connection current controllable. We can keep it safely under 250 amps. That keeps our connector, fuse, and switch costs manageable. The moment you jump to 300 volts, those component costs just spike.
Okay, next up, chemistry. Given the absolute mandate for low cost and that non-negotiable zero thermal propagation rule from China, we're left with LFP and sodium ion. This is our dual-track strategy.
LFP, lithium iron phosphate, is our default. It's the mature option. It's highly stable. It currently offers a pack energy density around 140 to 170 watt-hours per kilogram, which is plenty for a micro EV. And cost-wise, projections for 2025-2026 put LFP pack costs right around $70 to $80 per kilowatt-hour. So our $100 target is realistic.
But LFP has that well-known Achilles heel. It could derail our whole market entry in cold climates.
It's the performance in the cold. It's a severe weakness. At minus 20 Celsius, LFP's capacity and power output just plummet. So to mitigate that, you're forced to integrate complex and expensive heating systems, heating films, extra sensors, control logic, which draws power and adds complexity, and it pushes you away from your cost target.
And this is where sodium ion, or Ne-ion, becomes not just a backup, but an essential option for strategic flexibility. Where does that tech stand today?
Nion is emerging very quickly. The current pack densities are a little lower, maybe 100 to 160 watt-hours per kilogram, but they're improving fast. But its strategic value is overwhelming. Cost projections, once you scale up production, are potentially under $50 or $60 per kilowatt-hour. It's a fantastic price hedge. And critically, it gives you supply chain stability against the volatile price of lithium carbonate. Sodium is abundant and cheap.
But the real advantage for us for this micro EV segment is the performance in the cold and the system-level cost saving that comes with it.
Absolutely. Sodium ion has vastly superior low-temperature performance. It retains over 90% of its capacity at minus 20 Celsius. So our strategic decision is clear. LFP is the cost-optimized default for temperate regions, but sodium ion is the mandatory option for cold climate markets, Northern Europe, Canada.
Because you save money on the system level.
Exactly. By using neon in those cold regions, you potentially lower the overall system cost by completely eliminating the need for those complex LFP heating systems. You just skip all that hardware.
And regardless of which chemistry we pick, the form factor is non-negotiable based on our benchmarking.
We have to mandate prismatic or short blade cells. These forms are engineered specifically for CTP integration. They offer the best assembly efficiency and the highest volumetric density, which is paramount for a micro EV.
Let's talk thermal management. We've established liquid cooling is too expensive, but we have that non-negotiable zero propagation mandate.
Yeah.
So how do we get maximum safety with a minimal budget?
We reject liquid cooling. It's too complex, pumps, valves, hoses, and just too expensive. Our recommended solution is reinforced forced air cooling combined with thermal structural adhesives, the marriage of passive components and active cooling when you need it.
Okay, break that down. How does this system manage heat during a fast charge?
So we mandate using the aluminum alloy casing itself as an active heat sink, relying on natural convection and forced air. Structurally, we require those aerogel thermal pads between the cells. That's our fire break.
Right.
And then to manage normal operating heat, we apply a thermal structural adhesive to the bottom of the cells. This adhesive efficiently conducts heat away from the cell and into the cooling plate or the box structure where the forced air system can get rid of it.
And the BMS has to play an active preventative role here, right, to stop problems before they start.
Critically, yes. The BMS has to implement a strict charging deaeration strategy. We have to limit charging power when any cell temperature goes above 45 Celsius and completely cut off the charging current if it exceeds 55 Celsius. This hard limit prevents the thermal stress that leads to cell degradation and potential thermal runaway.
And for those cold export markets where we might still use LFP before we switch to neon, How do we handle the cold start?
We mandate the requirement for integrating thin film heating elements, heating films, into the pack structure, but these elements cannot be powered by the car's own battery. That would just kill the range and frustrate the customer.
But they're powered by the charging station.
Exactly. They are powered by the external charging station during a preheating cycle. It's the most cost-effective way to get an LFP battery ready for cold weather operation while preserving the car's driving range.
This is where it gets really interesting. We've gone from high-level strategy to concrete component decisions. But I have to ask, we've mandated aerogel, explosion-proof valves, secure elements for the passport, and now we're demanding 150 amps of DC fast charging capability. Are we sure we haven't just designed a very small, very expensive, high-voltage battery? How do we keep the BALUM under that $1,200 threshold?
That is the right question, and the answer lies in the strategic choice of the 96V 150V architecture. Every one of those safety and performance additions adds cost. But by selecting 96V, we are realizing massive downstream savings on the power electronic savings that outweigh the cost of aerogel and a secure MCU. We are counting on the commodity pricing of 250V components and the efficiency gains of CTP to compensate for the necessary safety mandates. It's a net zero increase on the BBUM, provided we execute the architecture perfectly.
Understood. The architecture itself is the cost-saving mechanism. Now we convert all of this architectural strategy into the final technical checklist for the engineering team.
The SOR.
The SOR. This section is the moment of truth. We need quantifiable, measurable, unambiguous mandates. Let's start with physical protection, the mechanical and structural mandates.
The protection rating is fundamental. We require dual compliance. First, IP67, which means the pack has to survive 1 meter of water immersion for 30 minutes. Second, and much stricter, is the IP69K rating. That certifies resistance to high-pressure, high-temperature washdowns, essential for cars in tough, dirty urban climates.
And back to that China safety revolution, the bottom of the pack has to be protected against road hazards.
Correct. The ESS has to pass the GB 3 Euro 31 2025 mandated bottom sphere impact test. It simulates road debris or scraping, which is a common failure mode for low-slung packs. And it has to do that without triggering a fire. And for long-term durability, we mandate compliance with ISO 124053 and the UN R100 Annex 9 random vibration spectrum. The pack has to hold up under years of road pounding.
And we talked about directional venting. What are the specific design requirements to guarantee that containment doesn't endanger the occupants?
So our venting strategy requires dedicated explosion-proof valves designed to burst at a specific internal pressure. But more than that, we have to design specific, controlled exhaust channels that are sealed from the vehicle body. This guarantees that any ejected hot gas or particulates are channeled downwards and away from the cabin and the high-voltage connections.
Okay, moving to electrical performance. We need to guarantee safety throughout the whole life cycle.
The standard for isolation resistance has to be robust. While the U.S. standard requires 100 ohms per volt after a crash, our design standard needs a big safety margin. We mandate that the ESS must maintain a DC isolation resistance of greater than 500 ohms per volt throughout its entire life.
A five-fold margin.
Exactly. It's essential for long-term safety. And for standard safety circuits, you can't overlook them, even in a cost-optimized car.
They're non-negotiable.
Absolutely. The high-voltage interlock loop, the HVIL, must be present and verified in all high-voltage connectors, and critically in the maintenance service disconnect switch, the MSD. If anything is open or compromised, the HVIL has to instantly command the main relays to open and de-energize the system.
And for charging, consumers want speed. How fast does the system need to pre-charge?
The pre-charge time has to be fast, imperceptible to the user. We specify less than 500 milliseconds for pre-charge, bringing the busbar voltage up to 95% of the system voltage before the main contactors close.
And we're setting a high bar for DC fast charge capability.
Our ESS has to support a maximum continuous current of 150 amperes. This allows for a competitive charge time, specifically a 30-minute rapid charge to 80%, which keeps us relevant in the market.
Now let's talk brains. The BMS software and functional safety. Cost is king, so which BMS topology makes the most sense?
We mandate a centralized BMS architecture. For a system of this voltage, a centralized approach integrating the control unit and the cell sensing modules onto a single PCB, it eliminates expensive internal communication harnesses, it maximizes cost efficiency, and improves reliability by removing failure points.
And that cost theme continues with cell balancing. Active balancing is superior, but it's way too expensive.
So we specify passive balancing only. This just uses simple resistors to burn off excess energy. Modern LFP and future neon cells are highly consistent, so a small passive balancing current of 100 to 200 milliamps is enough to maintain cell health without the huge expense and complexity of active balancing. We're betting on cell quality here.
And the functional safety requirements under ISO 26262, you can't skimp on those.
Critical functions have to meet the Automotive Safety Integrity Level C rating, ACC. This is a high integrity requirement, and it specifically includes the voltage and temperature sampling circuits and the control of the main relays. A failure there is an unacceptable safety risk.
And with the EU battery passport, cybersecurity is now a fundamental requirement to prevent tampering.
Exactly. Under UN Regulation 155, the BMS has to feature Secure Boot and COC, which is Secure On-Vehicle Communication Encryption. Secure Boot prevents unauthorized code from running, and COC is vital to prevent hackers from tampering with the mileage or the state of health data to inflate the car's resale value.
The BMS also has to act as an incorruptible black box, right?
Yeah.
Especially for a thermal event.
We mandate the BMS serve as a persistent data logger. It has to store detailed diagnostic data at a high sampling rate over 10 Hz for the 30 minutes before a failure and the 10 minutes after. This data is essential for post-mortem analysis and warranty claims. It's a non-negotiable feature.
And finally, what's the required accuracy for the state of charge, the SOC? This is famously difficult with LFP chemistry.
SOC accuracy has to be strictly maintained at less than 5% error over the entire lifespan. And you're right, it's hard because LFP's voltage curve is incredibly flat. A tiny voltage change can be a huge change in charge. So we achieve this accuracy by mandating a sophisticated algorithm that combines open-circuit voltage estimation, ampere integration, and crucially, a Kalman filter for predictive refinement. That's how you give the customer a reliable range estimate.
This is a tremendous amount of detail, covering everything from crash protection to data encryption. But meeting the requirements isn't enough. We have to guarantee future competitiveness.
That brings us to part 5, the strategic development roadmap.
The ultimate success of this whole project rests on hitting that cost target, under $100 per kilowatt hour. For our 15 kilowatt hour pack, that means a total bill of materials under $1,200. What does the market data tell us about achieving this, and where do we source our materials?
Well, the data from Bloomberg NEF indicates LFP pack prices have already dropped to $81 per kilowatt hour, or even lower in some large-scale applications. So our target is achievable, but it leaves almost zero room for error or luxury components. And to maintain that cost, we can't just rely on the most expensive Tier 1 suppliers.
Which means we need a robust Tier 2 and Tier 3 focus, leveraging suppliers who specialize in high-volume, cost-optimized LFP and sodium-ion production. Who are our strategic partners?
Our supplier strategy has to target those cost-optimized Tier 2 leaders. So Goshen High-Tech, whose JTM Jelly Roll to Module Tech is perfect for micro-EVs. They're already a key supplier to Wuling and Geely. We prioritize SVLT for their short blade tech, which we know offers superior safety and packaging. And finally, RPT, who offer fiercely competitive pricing and are widely used in low-speed applications.
And for our strategic sodium-ion hedge, which de-risks our supply chain and helps us enter cold climates, who are the key Tier 3 partners we need to be building relationships with.
For sodium-ion, we focus on partners like Hina, that's Zonka Heine, and Ferasis, or Funeng. And crucially, both of these suppliers have already verified their sodium-ion systems in actual vehicles from manufacturers like JC and JMEV. So they've moved out of the lab, which de-risks our transition by proving real-world integration experience.
Okay, let's just revisit that sodium-ion cost hedge one last time. If LFP is already hitting $80 per kilowatt hour, why is nylon still so important for system-level cost?
The strategic value goes way beyond the cell price. Nylon provides essential stability against lithium price volatility. But the real system saving comes in cold climates. By eliminating the complex heating elements, the control circuits, the insulation, and all the protective software you need to run LFP efficiently at -20 Celsius, the overall system cost of a nylon pack for those markets can be inherently cheaper. We just skip multiple components and integration steps entirely. It's a huge win for the BLOM.
Okay, let's wrap this up with our 4 key strategic recommendations, the non-negotiable future roadmap for our teams.
Strategy number 1 is the short blade plus CDP platform design. We have to abandon the traditional heavy VDA module standard. It just wastes space and structure. Adopting CTP with short blade cells maximizes volumetric efficiency, which is absolutely critical in a micro EV. And it also uses that long cell surface area for the passive air cooling we mandated.
Strategy 2 directly addresses our dual-track chemistry decision, sodium-ion compatibility without redesign. We need that flexibility to enter different markets without a multi-million-dollar hardware redesign every time.
That means building a highly adaptable BMS. The voltage sensing range has to be explicitly designed to accommodate both LFP, which has a nominal voltage of 3.2 volts, and sodium ion, which is a little lower at 3.0 volts. So we mandate a sensing range of 1.5 volts to 4.0 volts. This generous range lets us switch chemistries based on the market LFP for hot climates, Nanion for cold, using the exact same BMS hardware and casing. That is true future-proofing.
Strategy 3 is about tackling that huge regulatory weight of the EU battery passport proactively.
We mandate native battery passport integration. The team has to treat the EU regulation not as some aftermarket software fix, but as a foundational design requirement from day one. We integrate the carbon footprint model directly into the product lifecycle management system, and we ensure the BMS hardware supports encrypted signatures and secure boot. This proactive approach creates a powerful long-term non-tariff barrier advantage over competitors who try to play catch-up later.
And finally, Strategy 4 addresses a new commercial model for fleet applications, exploring swapping for B2B.
For fleet operators, logistics companies, rental versions, range anxiety, and asset depreciation are major operational hurdles. So we recommend pre-engineering modular interfaces, conceptually similar to CTL's EvoGo chocolate blocks, to enable potential battery swapping. This allows for rapid replenishment, eliminates charging downtime, and gives better fleet management. It significantly improves the business case for B2B adoption, and it adds a whole new market segment for minimal pre-engineering cost.
That was a tremendous deep dive. We went from global regulatory theory straight through to component selection and the final bill of materials target. To summarize for our listener, we face this intense and contradictory regulatory pressure. You have the zero propagation mandate from China demanding total containment.
And the digital passport data requirements from Europe demanding total transparency.
And that pressure, combined with benchmarking Wulling's cost ruthlessness, led us to our core architectural choices.
The cost-optimized 96V to 150V platform, the flexible LFP and Nanite-on dual-track, mandatory short blade cells, and the high-efficiency CTP structural design.
So what's the big conclusion for the industry, for any engineer stepping into this space?
The micro to low-speed EV market is no longer defined by low-quality products built to just scrape by. It is transitioned. It is now a highly technical, serious engineering contest defined entirely by compliant affordability. We've proven that meeting the highest global safety standards and the toughest cost targets are no longer mutually exclusive as long as you make aggressive, strategic choices rooted in commodity pricing and efficient integration.
And the ultimate recommended pathway for our engineering team to ensure that rapid global deployment and cost stability.
The priority development path is a 115V LFP short blade CTP system. It uses passive balancing and a centralized BMS with the structure and electrical systems ready for a seamless sodium-ion chemical substitution. This platform maximizes current cost savings while achieving immediate global market compliance and future flexibility.
So here's something for you, the listener, to mull over as we conclude today. We established that sodium ion has this vastly superior performance in extreme cold, retaining over 90% of its capacity. That's a feature that lithium ion requires expensive and complex hardware to match.
So, given this regulatory focus on data, carbon footprint, and total lifetime system cost, how quickly will the consumer adoption of sodium ion accelerate globally if its primary system-level advantage isn't just a slightly lower cell cost, but rather its vastly superior performance in extreme cold? A feature that lets manufacturers skip the complexity and expense of LFP heating systems entirely. If the system-level saving is greater than the cell-level saving, Neon could rapidly become the cold climate standard.
Food for thought indeed. Thank you for joining us for this deep dive into the future of compliant, affordable EV engineering. We'll see you next time.